In the last class, we have seen that any rotating system or any rotor can be completely balanced with the help of only two balancing masses placed at any two chosen balancing planes. Today, we will take up analysis of such rotating systems and to find out the masses which are needed to balance such a rotating system at the design stage. So, let us take a rotating shaft that carries n number of unbalanced masses. Let the planes of these unbalances be 1, 2 and so on up to n. When we view from this side, the angular position of these unbalances are for example, theta 1 from a reference which we can take as the vertical direction, and this is m 1 e 1, say this is m 2 e 2, making an angle theta 2. Let this be m 3 e 3, making an angle theta 3 and so on. So, let this be m n e n, making an angle of theta n, theta n. So, the angular position and the magnitude of unbalance at these positions are all known. Now, say for example, we have to place two balancing masses at some two chosen planes, depending on the convenience of the designer, that where such balancing masses can be placed physically. So, let this be one of the balancing mass we call 0, and let this be another balancing plane which you can call plane n plus 1. One other thing which needs to be taken care of is the distances of these planes where unbalances are present from the one balancing plane. For example, this is, in this case it is this one, so let these be the distance along the axis of the rotor from one of the balancing planes, let the 0th balancing plane. This and these are the planes where we have to place the balancing masses. So, now we have a complete idea about the configuration of the system. We have two balancing planes and we have the planes of the system where the unbalances are present, whose magnitudes and the angular orientations with respect to some reference. In this case, we have chosen this as the reference. They are all known. Our problem is to find out m 0 e 0 and m n plus 1 e n plus 1 placed at these two planes, balancing planes, and the values of theta 0 and theta n plus 1, so that the system is completely balanced. When we say completely balanced, what we mean is that there will be no unbalanced resultant inertia force and there will be no resultant couple due to these inertia forces about any point. Now, the problem can be handled in two ways. We can solve the problem by an analytical approach or we can discuss or we can solve the problem in a graphical manner. So, the graphical manner gives a better physical understanding. So, therefore, first let us take the case where we discuss or solve the problem by a graphical approach. Now, before we take up the problem, so let us consider one important aspect. Say if this be the shaft and this be one plane where the mass is here, that means its centrifugal force will be here at an angle theta. So, what will be the moment of this about a point say here? Where this distance is x. Now, since we are plotting this force or drawing this force as viewed from this, we should also draw the moment vector diagram also from the same view. That means, how the moment vector, that means the moment due to this force F at point O, how it is going to look. Now, you know that we generally follow the right hand screw rule. So, following that rule, you know, in this view from this direction, the moment vector will be, if it is in this direction, then moment vector will be, you have to stretch your imagination little bit, and this will be the moment vector which magnitude is nothing but f into x, but it will be at right angles and in this sense, in a clockwise sense, leading the force vector. On the other hand, if the point is here about which you are taking the moment O prime and this is the force or distance x, then the moment of this force as seen from this direction will appear as a vector which is lagging behind this force vector. So, therefore, what we can say that we can ascribe a sign to this quantity x when the force or the force is towards left, we can consider such x values as negative, and when it is towards right, we can give this quantity a positive value, and the moments will be all leading the force vector by 90 degrees in the positive sense. If the moment is negative, because the x is negative, then obviously it will be diametrically opposite to that. That means, it will be lagging the force vector by 90 degrees as shown here. So, this thing has to be kept in mind when you solve the problem in a graphical manner. Next, let us go to the solution of this problem. Now, you see how many unknown quantities we have. If you see, we have two forces or two unbalances m n plus 1 E n plus 1 and m 0 and E 0 to be determined. That means, two quantities, but it is not only the magnitudes, it is their angular positions theta 0 here and theta n plus 1 have to be also determined. So, when you draw a vector diagram, the resultant is 0 if it leads to a closed polygon. So, therefore, if we draw the forces, then you will find we can draw the side view of the forces, force vectors will be something like this. Now, all these terms will be multiplied by omega square, and since it is going to be same for all, what we propose to do, we omit this term omega square from all these vectors. So, simply m1 u1 can represent the unbalanced force, then m2 e2, next m3 e3, and so on. There may be many, and finally, we may have mn en. Now, when we add the two forces generated by the balancing masses at this plane 0 and n plus 1, that means there will be two more vectors which we do not know neither the magnitude nor the direction, say m0 e0 and mn plus 1 en plus 1, both are unknown. So, we cannot draw this force vector diagram. On the other hand, if we consider the moment vectors, what happens? Moment always depends on the point of, that is point about which moment is taken, and that point is at our disposal, we can choose it. And we also know that moment of a force about a point through which the force is passing is 0. So, we can always eliminate one unknown by choosing one of the balancing planes, for example, in this particular case the 0th plane as the reference about which the moments are to be taken. So, when we draw or take moment about this point, then the moment of all the unbalanced forces except the balancing force or balancing mass produces in the plane n plus 1, rest are all known. So, only one unknown is involved, and we can draw the moment vector diagram. So, therefore, first what we will do, we will draw the moment vector diagram. Now, you can see one thing, that all the moment vectors are going to be either leading the force vector by 90 degrees, the corresponding force vector by 90 degrees, or lagging the corresponding force vector by 90 degrees, depending on whether the plane where the force is being generated is on the right hand side, that is x is positive, or on the left hand side, that means x is negative. Now, since this is the case, what strategy we can take to make our life easier, that we draw the moment vectors are also along the force vectors if the planes are on the right hand side, and opposite to the force vector if the plane is on the left hand side. So, thus what we will do, we will draw the moment vector also in this, and the whole thing actual moment vector diagram will be obtained by rotating the whole system as a rigid body by 90 degrees. So, this will be the moment due to the unbalance in the let us start from 1. Now, since plane 1 on the left hand side x is negative, we will have the first moment opposite to this, because x 1 is negative. Similarly, m2 e2 x2 will be also opposite to this because x 2 is negative. But I think if we go to 3, then you will find it will be in this direction if the balancing plane or plane of unbalance be on the right hand side. Let so this becomes M 3 E 3 x 3, and similarly we keep on going. So, finally, we come to this as M n E n, and if the couple balance a couple has to be balanced, then this must be M n plus 1 E n plus 1. So, what we have got is this, that we have got the magnitude and direction of the couple which needs to be generated by the balancing mass placed at n plus 1. So, magnitude is given by this, sorry. So, since the magnitude is known, so M n plus 1 E n plus 1 is determined. Again, since this plane is on the right hand side, that is it is x n plus 1 is positive, then the force vector, that means the theta n plus 1 will be also obtained from this as this. Thus, one of the unbalance, that means one of the balancing mass to be placed, both the magnitude and angular orientation is determined, and we know that it has to be like this. Once this is known, we can then proceed to draw the force vector diagram, because now only one force is unknown, that is the balancing mass placed at plane 0. So, to do that, we have to now draw the force vector diagram. This is the moment and the moment force vector diagram will be, again we start from 0, this is M 1 U 1, M 2 E 2 will be in this direction, M 3 E 3 will be in this direction, then we have two more as placed here. This is M n E n, and even this one is known. So, to close the polygon, your M 0 E 0, which is the only other one force left, must be this. So, again you find that we find out its angular position theta 0 and its magnitude m 0 E 0. Thus, m 0 E 0 is determined and of course, theta 0 determined. So, we have solved the problem, though we have taken a particular case, but it is fairly general and any rotary balancing problem can be handled in this way. Now, of course, it has given us better physical insight and sometimes the solution also is quick, but as we know that graphical procedure is having some inherent disadvantage, that means accuracy of the results what we get will be always subject to your measurement, drawing and such things. And if a problem has to be done on again and again repeated on trial and error basis, then again graphical procedure is not a very convenient one, and in these days of computers we should go for analytical approach. So, next what we do, we discuss the approach by using an analytical technique to find out these 4 unknown quantities. The problem is the same. Again, in the analytical approach, we should keep in mind that our primary objective is to place balancing masses in these 2 planes of such magnitude and of such angular orientation that the total force generated due to rotation, or that is the centrifugal force, that is the inertia force, is 0. That means, total inertia force generated vector sum will be 0 and the total moment of all these inertia forces is also 0. That is the requirement for any dynamic balancing. So, this we have to keep in mind. Now, here once we know that if the vector is 0, that means resultant vector is 0, then we should also keep in mind that if we resolve this resultant in 2 directions, the components will be also 0, or in other words that if we sum up the horizontal or say x components, vector sum of x components say I and vector sum of j components y components j is 0. And this will be 0 if and only if both the sum of the x component is 0 and sum of the y components are 0 individually. Same is the case here also, that if we take the x components of these moments, that sum will be also 0, y components of the moments will be also 0. So, by the same logic, so we will get 4 equations and we have seen that we have 4 unknowns, m 0 E 0 and theta 0 and m n plus 1 u 1 n plus 1 and theta n plus 1. These 4 quantities, these unknown quantities can be determined by solving these 4 equations. Normally, we take a tabular approach to make the whole process look more systematic, and that is what I will just explain now. So, the columns are, first column is indicating the plane in which the mass is there, x is the distance from the reference plane, which in most cases we select as the 0th plane, that is one of the balancing planes. So, to indicate that, maybe we should put some kind of a star, that these are the balancing planes, where you have to decide the masses. On the other hand, the other ones are given. So, x for this, of course, x will be 0 in this case. In this case, it will be x 1, x 2, x 3, x n and x n plus 1. All these quantities are known, no problem. Here it is m 0 E 0, m 1 E 1, m 2 E 2, m 3 E 3, and what you have to determine is, so this and this are to be determined. Here it will be obviously 0. Now, of course, I have not put here, I should put somewhere here theta also. So, it will be theta 0, theta 1, theta 2, theta 3, theta n plus 1. Here theta 0 and theta n plus 1 are not known. So, therefore, the unknown quantities are what I will mark. The unknown quantities are, this is the unknown quantity, this is the unknown quantity, this is the unknown quantity, and this is the unknown quantity. These 4 quantities are to be determined. So, now here of course, couple it will be 0, this component will be 0, this component is also 0 because m e x itself is 0. Here it will be m 1 u 1 x 1 sin theta 1, here it will be m 1 e 1 x 1 cos theta 1. Here of course, it will be m 0 e 0 sin theta 0, here it will be m 0 e 0 cos theta 0. Next one will be m 2 e 2 x 2 sin theta 2, be m 2 e 2 x 2 cos theta 2, and of course, this is m 1 e 1 sin theta 1, m 1 e 1 cos theta 1, m 2 e 2 and this will go on. It will be m n e n x n sin theta n, this will be m n e n x n cos theta n, this will be m n e n sin theta n, this one will be of course m n plus 1 e n plus 1 x n plus 1 sin theta n plus 1, So, our table is complete. Now, as I have always done earlier, let us mark the unknown quantities. Of course, this is an unknown, and since this is an unknown, this is an unknown quantity, and this is an unknown quantity. This is an unknown quantity. This is an unknown quantity. Okay. So, as you can see that from these 4 equations, what it means that this sum should be equal to 0. This is the couple x component. This is one sum, the cosine component of the couple, it should be also 0. This is the sine component of the force, should be 0. This is the cosine component of the force, should be 0. Here of course, we have taken this as the x and this as the y components. Now, if we sum up this and make it 0, so you can find that we get an equation with only one unknown term. So, this equation will give us that m n plus 1 e n plus 1 x n plus 1 sin theta n plus 1 is equal to minus m I e I x I sin theta I is equal to 1 to n. All of these are known quantities. So, this is determined. Similarly, because the sum is 0, so we get from that equation. Similarly, the other component of the moment is also known say this is equal to A and say this is equal to B. Hence, we can say that m n plus 1 e n plus 1 x n plus 1 is equal to square root of a square plus b square, squaring the two term and adding, and this will give us which is a known quantity. Since x n plus 1 is known or given or chosen, we know the actual unbalance or balancing amount to be placed in the n plus 1. So far as the magnitude is concerned, we have found it out. We can also find out the angular position from this dividing the two. So, from this theta n also n plus 1 also is determined. Thus, this is also determined. So, from the column or two columns showing the components of the couples, they give us one unbalanced mass or balancing mass and its angular position. Once that is done, then from the force columns, then this becomes already known, because m n plus 1, E n plus 1 and theta n plus 1, they are all known quantities. So, this is known and this is known. So, from this equation and this equation, what remains, only one unknown is there, and we can write is equal to minus sum total of I equal to 1 to n plus 1. Say let us consider this is as C, and the cosine component let this be D. So, they are now known, and therefore, these two will give us m 0 E 0 equal to square root of c square plus d square, and tan or rather theta 0 equal to tan inverse c by d. So, both this and this gets determined. So, you can see that following an analytical procedure explained in the form of a table, we can find out the 4 unknown quantities, that is the magnitudes of the balancing amount to be placed in the two balancing planes and their relative angular positions. They are all found out in this manner, and here obviously the answers will be more accurate, because we have followed an analytical procedure. So, this is the way at the design stage, when the designer knows the kind of various objects are coming and the centers of mass of the various components coming, it is possible by the designer to identify two suitable balancing planes and to put suitable balancing amount, so that the whole system is completely free from any unbalanced inertia force. Another kind of problem which needs to be discussed is that when we are given a rotating body. Now, if a rotating body is given to us, sometimes it may be necessary to take care of its unbalances, which are produced by some errors in manufacturing, some misalignment during assembly, and such problems. And in such cases, we have to take these bodies either to a machine where we can put the rotor or rotating system and do experiment to balance it, or sometimes we may take the approach that going to the location where the rotating object is present and try to do some experiment in balance. So, in the first case, we take care of the balancing procedure with the help of some machines which we call balancing machines, and in the second case where you do not use any machine to put the rotor on that, but we go to the field to do the balancing there itself, we call that procedure as field balancing. In the next lecture, we will take up these two aspects.